Good day, everyone. We are welcome back to my channel, Spark Scholar. In this series, we have been discussing machine, and in today's class, we will be discussing transformer. Right? We'll be discussing transformer, and we have done. This is actually the third video in this series. The first video was mainly about the evolution of transformer and the basic classification of transformer, and also we discuss DC machine. Sorry, classification of what machines. Then we discuss DC machine. While in the second video we discuss AC machine, and this is the third, which was supposed to be part of that second video, because we'll be discussing what the transformer, we still fall under what this AC machine. Now, the basic things that we are supposed to know before starting the class is what is a transformer. In our previous class, we have already discussed why transformer was classified, or why transformer is classified into AC machine. So if you want to know the basic reason why we are classifying transformer as a type of machine, then check my previous video on AC machine. Now, what is a transformer? Using what a simple and basic definition, a transformer is a static electrical device used to transfer electrical energy from one circuit to another through a changing magnetic field. Normally, a transformer work with the principle of what it's either you call it what mutual induction or electromagnetic induction. Yes, it uses what Faraday's principle. Faraday principle of what electromagnetic induction to operate. That is what is principle of what operation. Now we say a transformer is a static electrical device because transformer does not move. The basic part of transformers, they are all static except what the magnetic flux. So it does not move. So we call it what a static electrical device. Yes. It usually consists of two or more coils. It usually consists of what two or more coils of wire wound around a common magnetic core. Normally for a transformer, you have what a core, you have a core where you wound your wire. Now we have what magnetic wires here. So we have wires that are wound on this coil. Then we have another wire. But looking at this one, these are just a set of wire, right? The primary and the secondary. But there are some transformers that they have more than one coil. But for this basic one, you're having a core and we having what a wound wire. So a transformer has no internal moving part. Yes, it does not have what any internal moving part. It operates based on the principle of what electromagnetic induction, especially what mutual induction. Through this principle, electrical energy can be transferred from one coil, from the primary coil to the secondary coil without direct electrical contact between the coil. Now looking at the coils of a transformer, they are not physically linked together. They are not physically connected. What they normally use, like how the secondary normally induce voltage coming from what the primary circuit is from what electromagnetic induction. Now, the principle of operation of a transformer is this. The operation of a transformer is based on what the Faraday's law of what electromagnetic induction. According to this law, when changing magnetic flux linked with a coil, an electromotive force or EMF is induced in that coil. So in a transformer, an alternating current is supplied to the primary winding. This alternating current produces an alternating magnetic flux in the iron core. Though the magnetic flux link with the secondary winding, thereby inducing an EMF in the secondary coil. This process is called what? Mutual induction. And we know mutual induction. So therefore a transformer works because a changing current in one coil produces a changing magnetic field, which then induces a voltage in another nearby coil. Now this is a circuit for what a basic transformer. So the primary windings, a basic single phase transformer consists of two main windings. We have the primary winding, which is connected to your supply or to your source. Then we have what secondary winding, where your load is connected to. So the external circuit, the primary and secondary windings are not electrically connected as you can see. However, they are magnetically coupled together through this what transformer core. Right now, the current that is entering the primary side is the primary current, while the secondary going out from the secondary side is called what the secondary current, and this is what our load. Now, transformer core. The windings of a transformer are wound around what a common magnetic core, usually made up of soft iron or silicon steel. The core provides a low reluctance path for the magnetic flux. The core is usually made up of thin sheet called laminations. Now, these are what our transformer core, as you can see here. This is a part, or this core is what is providing a path for the magnetic flux generated by the primary winding to go to the secondary what part. So once this magnetic flux flow through this transformer core, then those magnetic flux will be caught by what the secondary winding, and EMF will be induced in this secondary what secondary side, known as what electromagnetic induction or what mutual induction process. So now, why are transformers important? Transformers are very important in the generation, transmission and distribution of what electrical energy. One major reason alternating current or AC is widely used in power system is because AC voltage can easily be transformed from one level to another. And looking at it, let's talk about the generation. Now, uh, the generating stations that we have is somehow distant from what is the load center. Now, when citing what is generating station, you cite generating station based on your resources, or based on the raw materials that are needed to make that generating station to work. Now, you don't just come and say, oh, okay, this is a load center, you want to site the generating station very close to the load center, when the resources or the raw materials that you need to run that generating plant is not close to that load center. Now we have different many generating plant in Nigeria. One is located in Shiroro, known as Shiroro Power Plant, and it's hydro power station, which means that generating station was located there because of what the source of water that is there. Now after generating, like the generation that normally take place in Shiroro Power Station, they are generating at 16 kilovolt. Yes, 16 kilovolt. Now they don't transmit that 16 kilovolt. To then send it to the load center, they have to transmit it. First of all, they have to send it what to the switch gear. From the switch gear, then they transmit it to other part of what Nigeria that we need it. Now that 16 kilovolt is too small, the voltage is too small to be transmitted because the losses will be very high. Now since the voltage is low, then definitely it means the current will be very high. Then I square arrow, which is what yes, I square arrow losses, that is the power losses that is coming out in form of heat, will be very high. So to reduce this voltage, they will need what is called what a transformer to step up the voltage so that the current will be reduced, right? So they reduce the current and step up the voltage to around 330 kilovolt or 132 kilovolt, depending on the type of transmission line they want to use. Then also when you come to your distribution section, now after the electricity have been transmitted, then the transmitting voltage is too high for consumers to consume, so they need what a transformer to step it down again to the voltage that they can consume. And the distribution voltages that we know in Nigeria are either 33 kilovolt that can be run directly to, let's say, our industries, or 11 kilovolt, right? 11 kilovolt. And once now 11 kilovolt are the distribution voltage that is mainly sent to residential or commercial apartment. Now you also need a transformer there that will step down 11 kilovolt to either 4153 phase or 230 volts so that the consumers will be able to use it. Now, as we all know, our power is what? Voltage multiplied by current, right? Now, for the same amount of power, if the voltage is increased, the current decreases for power losses in transmission line. It's given by this. The P loss is I square R, like what we have said earlier, I square R. Now, for you to have what? A lower current, then it means you have to boost up or you transform the voltage to a high voltage to reduce what this power loss. We have already discussed that. Now voltage transformation. A transformer can either increase or decrease voltage. This is where types of transformer come in, where you will be having like a step up transformer or a step down transformer, because it's either you are increasing or you are decreasing the voltage. And once you are either increasing or decreasing the voltage, opposite will occur to the current. When a transformer increases voltage, it is called what? A step up transformer. And when transformer decreases voltage, it is called what? A step down transformer. In both of these cases, the frequency remains constant. The frequency does not change. Now let's discuss the basic construction of what a transformer. The key parts that are found in a transformer. That this is what a basic transformer here. Now the key parts that are found in transformer or a simple transformer consists of the following part. One, we have primary winding. The primary winding is the winding that is connected to your supply. Two, we have secondary winding, which is connected to the load. We have the magnetic core, the iron part where your magnetic flux will flow through from the primary winding to secondary winding for mutual induction to take place. Then we have insulation. Insulation is what is used to separate the coils from each other so that they will not conduct. Then also we have lamination. Laminations, they are thin insulated iron sheets used to reduce eddy current losses. They are called what? Laminations. The working process of what a transformer, we have already explained that, which is what is a mutual induction process. We have already explained that, but for you to get more explanation, you can pause the video to read too. Now, electrical isolation in transformer. In a transformer, there is no direct electrical connection between the primary winding and the secondary winding. The two windings are electrically isolated from each other, but they are connected together magnetically through a common iron core. Because of this electrical isolation, a transformer can also provide isolation between two circuits. This is why transformer with equal primary and secondary voltages is commonly called an isolation transformer, because the purpose of that transformer is not merely to transform the voltages. It's not to either increase or decrease the voltage, but to act as what? An isolator between what? Two circuits. Now for a step-up transformer, it means the primary windings, the secondary windings is greater than the primary winding. When the number of turns in the secondary side is greater than the number of turns in the primary side, then you call such transformer a step-up transformer. Now, since the primary winding is greater than the secondary, since the secondary winding is greater than the primary winding, then it means the secondary voltage will be higher or greater than the primary voltage. So that is why this transformer is called what? A step-up transformer. You are sending in a particular voltage, it will step it up, it will increase the voltage. While for a step-down transformer, the secondary winding is usually less than the primary winding. Now, when the secondary winding is less than the primary winding, then it means the voltage, the secondary voltage is less than the primary voltage. So it means you are sending in a certain amount of voltage to be stepped down so that they will be able to use it. Like most of those transformer, most of those step down transformer are mainly those commercial transformer that mainly step, let's say those one that step our voltage down to either from 11 kilovolt to 415 three-phase system, or 230 to 240 volt single phase system. While for this step up, they are mainly used for before transmission. So you step it up, then to transmit, to pass through what very long distance. Then when you get to the consumer's end, then you can then step it down to what the consumer can actually what use. This means that secondary winding has fewer turns than the primary winding for a step down transformer. For isolation transformer, the secondary voltage is the same as what the primary voltage, because the secondary number of turns is the same with the primary number of turns, which means the turn ratio is 1:1. This type of transformer is called an isolation transformer. It is used mainly to electrically isolate one circuit from another while still transferring power through magnetic coupling, which is what using what electromagnetic what induction. Now, what is transformer turns ratio? Right? Turns ratio is very important in a transformer. Now, our NP is the number of turns in primary winding, while our NS is number of turns in secondary winding, just like for the voltage and for the primary voltage and secondary voltage also. Now, for our turns ratio, transformer turns ratio is the number of turns in the primary winding divided by the number of turns in the secondary winding. Right? The number of turns in the primary winding divided by the number of turns in the secondary winding. So for an ideal transformer, the number of turns in primary winding divided by the number of turns in secondary winding is the same with the number of turns in the primary winding divided by the number of turns in the secondary winding. You see the voltage here, voltage in primary divided by the voltage in secondary is the same as what number of turns in primary divided by the number of turns in secondary. Now this is for what? Our turns ratio. This means that the voltage ratio is equal to the turns ratio. Now the turns ratio shows how the transformer changes voltage. For example, if a transformer has a turns ratio of 3:1, right? 3:1, then it means this is what a step down transformer. It means this is what a step down transformer is, stepping it from what? 3 to 1, because normally you have what? Your VP all over your VS equals your MP all over what? Your NS. Now let's try to solve this to make it simpler. This is a step down. Okay, let's assume the primary voltage is 240, right? Then it means I should put 240 here. I'm looking for what? My secondary voltage equals, then here I have 3, which is my turn ratio, 3 all over 1. So it means my VS, if I cross multiply here, I will have VS multiplied by 3, then 240 multiplied by 1. Then for me to get my VS, I will have 240 divided by 3. So my VS is what? 80 volt. Then from here, it means my voltage was stepped down from 240 volt to 80 volt. So which means since my turns ratio is greater than 1, then the transformer is what? A step down transformer. Now a transformer changes voltage and current, but ideally it does not change the power transferred for an ideal transformer. Yes, we call it ideal transformer because normally there are losses that will take place in transformer. We have hysteresis losses. Let's say we have copper losses and we have core losses, right? In your core losses, we have different types where we now have hysteresis losses, eddy current loss and others. But for an ideal transformer, we assume the primary power is the same as what the primary voltage, right? So if they are the same, then it means we already know that my power is what? Voltage multiplied by current. Then it means the primary voltage multiplied by the primary current is the same as what? The secondary voltage multiplied by what? The secondary current. So this means that if the voltage is increased, current is decreased. Also, if voltage is decreased, current is increased. Therefore, a transformer does not create extra power. It only changes the voltage current relationship. So for a step down transformer, we already said the secondary voltage is greater than primary voltage. Why the secondary current will be less than the primary current? Yes, because the reverse is the case. And also for a step down transformer, the secondary voltage is less than the primary voltage, which means the secondary current should be higher than the primary current. Now, transformer ratio. Just like what we said before, transformer ratio, or you call it what, the turns ratio, is primary winding divided by what, the secondary winding, or the primary voltage divided by the secondary voltage. Now, if my alpha is greater than 1, then it's what, step down transformer. If my turns ratio is less than 1, then it's what, step up transformer. However, if my turns ratio is 1, it's called what, an isolation transformer. Then let's discuss about what, impedance matching, because impedance matching is also what, important. Yes, important. This is common in audio circuit, communication circuit, and some power applications. So the impedance transformer relationship is the primary impedance divided by the secondary impedance equals the square of the primary turns divided by the secondary turns, right? The primary turns divided by the secondary turns square, which means my impedance ratio equals my turns ratio square. That's what it means, right? Okay, now we are giving an example. A transformer has 1,500 turns on its primary winding and 500 turns on its secondary winding. Then from here, it means the primary turns is greater than what the secondary turn. Then let's check if this is what, a step down transformer or a step upward transformer. So we are told to determine the turns ratio. Looking at this, turns ratio equals the primary winding divided by the secondary windings. The primary winding is 1,500, then divided by the secondary winding, which is what, 500. So it means my turns ratio is what, 3:1. I will say whenever turns ratio is greater than 1, then that is what, a step down transformer, right? So we have already solved this question. So let's continue. I think we have already explained this in the previous slide. Or we can say take it, right? Because we have already explained this in previous slide, but we can see that this is our turns ratio, right? And this is our turns ratio. When we tend to what, cross multiply here, no, when we cross multiply, it will not give us what we want. But when we take it that okay, how this was formed is for what, our primary power equals to secondary what, power. Yes, our dp, which is a power at the primary input, which is the input power, equals what, to the output power. Then we have this. Then from here, if we are looking for one of them, let's say we are looking for what, the input voltage, we can decide to divide both sides by what, the input current. So transformer EMF equation. The EMF equation of a transformer gives the relationship between the induced voltage and the supply frequency, the number of turns, and the maximum magnetic flux in the coil. So a transformer operates on the principle of what, electromagnetic induction, as we have stated, when an alternating voltage is applied to the primary winding. An alternating magnetic flux is produced in the core. This changing magnetic flux link both the primary and secondary windings and induces EMF in them. So for a sinusoidal magnetic flux, we have this. This is the magnetic flux, and this how is denoted. That this is showing you that it's not static, but it's what is sinusoidal, or is what, dynamic. Here, this is representing what, our instantaneous magnetic flux. This is the maximum value of flux. This is what, our angular velocity, and our t is time in seconds. So induced EMF in a coil is given to be this, E equals to N the flux dt. Like this is what the induced EMF from a coil. Now, if our flux is this, then the flux dt, it means it should be this. So if you differentiate this with respect to t, it means you should be able to have this, right? If you differentiate this with respect to t, it means you should have this. Then recall our E is this, but then we have our E and represent, then remove the flux dt, which is this, then it means I will have what, this equation. Then the maximum value of what the induced EMF is E maximum equals n angular velocity, then multiplied by what, the maximum flux, right? E maximum equals this, and our angular velocity is 2 per f. Then if our angular velocity is 2 per f, representing, removing angular velocity and representing by what, 2 per f, we have what, our maximum energy to be, maximum induced voltage to be this. So we have this. While our what, RMS value of the induced EMF for a sinusoidal waveform is given by this, is what, the E maximum divided by what, √2. So our ERMS, we already got our E maximum to be this, then we can represent it with this divided by what, √2. I will know that 2 pi divided by √2, which is this, 2 pi divided by √2 is 4.4. So if it's 4.4, then it means I can remove this and this and replace it with this. So it means our ERMS equals 4.44 F number of turns, then the maximum flow. This is general transformer EMF equation, right, which is this. So the voltage ratio for the EMF and equation is this. So for our primary, we have this, while for our secondary, we have this. Don't forget, this is same as what our turns ratio. So if this is denoted the primary and this is denoted the secondary, then it means we should what, have this. The voltage induced in the secondary, in the primary divided by the voltage induced in secondary equals the primary turns divided by what, the secondary turns, which means our primary voltage divided by our secondary voltage is approximately our primary turns divided by what, the secondary turns. Then from there, our alternative form using flux density, we know our flux to be what, flux density multiplied by area, right? So it means for our maximum flux should be what, maximum flux density multiplied by area, and we already know our previous formula. So from our formula here, so we are removing this maximum flux and replacing it with what, this equation, which is what, flux density maximum multiplied by what, A. So this form is useful when the flux density and the core are known. So in summary, a transformer transfers electrical energy from one circuit to another through mutual induction. The primary and secondary windings are electrically isolated, they are not connected, but they are magnetically what, coupled or linked together. The output voltage depends on the ratio of the number of turns on the primary winding to the number of turns on the secondary winding. So if the secondary winding has more turns than the primary windings, the transformer is what, step up voltage, and it's called what, step up transformer. If the secondary winding has fewer turns, the transformer step down voltage, and it's called what, step down transformer. So if both windings have equal turns, the transformer acts as what, as an isolation transformer. So the main transformer relationship is this, which is what, your turn ratio. This shows that the voltage transformation depends directly on the turns ratio. So this is the end of our class for today on transformer. Actually, there are a lot of things that we are still supposed to discuss on transformer construction, and a lot of calculation about transformer, but because of time, we just have to stop here, wait for our next video. I will say bye. Bye. Don't forget to like and share this video to others that may benefit from it, and don't forget, Spark Scholar from idea to paper. Bye for now and have a nice day.